So, welcome. It's great to be doing the I4 Energy now intermixed with CITRIS, and this talk is touches on several different I4 Energy projects. I'll try to touch on some of those as we go. Carl and I have been working for the last couple of years to really make I4 Energy a place, a kind of nexus to bring together the information aspects of energy in a number, and this is certainly one of them. This talk actually began in NSF-sponsored workshop a couple of weeks ago, what I did with my spring break. NSF has supported the CyberPhysical Systems program now for several years, 3 or 4 years, and probably one of the largest investments, and that growing out of almost 10 years of DARPA funding. So they're in the role of transitioning this to NIST and creating a foundation for industry to pick up on it. So this was started out as part of steps towards a reference architecture for CPS, which means cyber-physical systems in grids and buildings. So what I've done with this talk is to spend just a couple of minutes to try to set a little bit of context, and in particular to touch on 4 sample drivers. So in a lot of this work, which is really about nuts and bolts of building operating for things that don't look like computers but have computers everywhere throughout them, is really to let that be driven by some applications that push the extremes of those. And then what I'm going to do is essentially just walk you through where we've ended up in our thinking of actually designing one of these. And so I've kind of intermixed that with the explanation. And there's a little bit of color coding. The blue background are the hand-wavy parts about the application where you can relax a little bit, and then mixed with essentially the representation of the design, and we'll talk a little bit about some of the current explorations as we push on out, and hopefully some time for discussions. So one form of teeing this up, as we think about the energy challenge, we've generally formulated it something like this. The 3 tiers: energy supply, transport, which is really transmission and distribution to the load, perhaps, and we know, the problem is to manage a portfolio of supply assets to meet a time-varying load. And sometimes as we get into information, we start talking about markets as kind of the extent of it. And if we look at what's happened, really that as a cyber-physical system, that piece is the physical plane of it. And, of course, the physical plane has changed as we've brought in fluctuating renewables, wind and solar, for example, and increasingly brought in storage, historically pumped hydro, but increasingly others. But, of course, that's not just on the supply side. We have fluctuating renewables and storage showing up on the load side. And, of course, what's really broken about this is it's not the end purpose is not to turn the motor on in the HVAC system. It's what you're delivering really to people on the far end. So in some sense, that 4th tier that's always left out of the diagram of consumption and usage and pricing. And today, within the grid, the feedback is real subtle changes in the actual signal, the voltage, frequency, and phase of electricity. Over there inside of HVAC systems, the feedback is pushback on the temperature of air and water in the media that is exchanged. Whereas going forward, all the feedback is going to come through that information plane that is yet to be created. So in some sense, the challenge for all of us, in some sense, is creating the information plane for the future grid. And that's really the question I'm looking at primarily from the point of view of that consumption side. And as soon as you look at that, the answer is pay a lot of attention to buildings. Why? Because that's where you're spending 70% of your electricity. So let's start with the role there. Okay, so in that context, part of what helped us in many fields, we identify model problems, things that are sort of examples of the larger problem. So for us, there's been a few of these. The first one, really, this notion of dispatchable demand. How is it that we can utilize the slack in the energy consumption chain, if you will, that supply, to balance fluctuating renewables? And we touch on this a little bit with demand response and things like that. What it means is, take advantage of a thermal mass, for example, in buildings, the electrical storage, for example, electric vehicles, phase change materials in refrigeration. The real, when you can get a hold of not doing something you would have done and shifting that in time is where you get this infinite gain on the amount of effort compared to the effect. So lots of different tools that we could begin to use to get the actual consumption side to exhibit a load that was more available. Of course, optimizing, in this case, buildings. We do that for energy efficiency, but just as well, perhaps more importantly, for comfort or for agility when you look at the first one. And that gets into integrated control, model predictive control, personalized conditioning, things like that. 2014 is the year of the Internet of Things. 1999 here at Berkeley, we said 15 years from now we will have the technology to connect all of the people on the planet, and we will be in the act of connecting all the things. Here we are 15 years later. That's precisely where we are. 30% of the world's population on the Internet, 92% of the world's population on a cell phone, and the next 10 billion devices without any question. So part of that is moving towards what does that mean beyond the hype? And what you see out of the Consumer Electronics shows is really about open systems for building automation and other things like that. Actually, another one that's come directly out of i4Energy is going back in and starting to put information in the grid itself, in particular microsynchrophasers. This is if you had time-synchronized phase angle measurements, can you actually get situational awareness across the grid and begin to react? And microsynchrophasers are pushing those from transmission to the distribution tier. Okay, so I'm going to use these as a bit of background and just begin to sort of walk through what it's taken to begin to solve the nuts and bolts question of creating an operating system for these kind of things. Without question, the biggest first step was to get to, if you will, the equivalent of what we did with the Internet and the web. So what the Internet did was allow us to deal with all sorts of different kinds of technologies, serving a variety of applications through a narrow waist. The web did that same kind of focus for the world's documents. And the question here has been tremendous variety of physical information, electrical, water, environment. Can we create a narrow waist so that you can deliver that information in a homogeneous way to a wide variety of applications? And that was some work Steve Dawson-Haggerty talked about here 2 years ago, essentially creating a RESTful stack to deliver that in modern web services. I'd say this piece with the simple monitor actuation profile has largely been done. There are other variants now, other work as well in this space, but without question, this is a part that's essential to get it going. What that meant as we began to go to say, how would you actually build an operating system, is you can think of SMAP as, in a way, the hardware presentation layer. So the analog here, and I want to explain diagrams. So I realize fairly general audience. In computer systems, we often will, draw these representations of things. The notion there, just as I look at the floor plan for my house, it doesn't describe everything about the design. It gives us a way of talking what are the major components and how do they hook together and where do we begin as we talk about the structural engineering and how do we construct the rest of it. There's a similar thing here that I want you to understand, that vast variety of different connections into the physical world, all kinds of devices, things that are part of HVAC systems, things that may be sensor overlays we deploy on those, all sorts of different kinds of interconnect. This lower layer essentially is like when I plug in that printer, how do you get the software that allows a document, any document, to show up on that printer, the set of drivers for it. A little more involved in this case because this is inherently a distributed structure that may be down inside of the building, whereas this may be a completely different wireless sensor network or some sort. So this tier of SMAP drivers have also given us a way of crossing this distributed set of information assets and elevating it. When we started, we talked about a physical information bus. So this was a kind of technology started in the 80s in things like financial processing, that you had an information bus, all of those different economic activities. You could see it, subscribe to the ones you cared about, take actions. Okay? And part of what was going in our thinking here was that actually, while we want all sorts of different uses of this information, it has quite a bit more structure. And those very complicated pub-sub solutions were probably overkill, and instead this was natural to formulate in a web services environment that the whole world has moved forward to in the last 30 years. So I'll touch only briefly on that. What's pretty clear is that there was also a set of higher-level system services. So this is the thing you take for granted today in your email and your Googles and all of the rest of the things that live out there, supporting a variety of applications that would be quite specific, and that what I'm going to do is sort of fill in more of the details of each of these pieces. So what the heck do I mean? So for example, in a building like this, there's a whole HVAC system that sits behind a building management system. There's another one that also speaks BACnet IP for lighting. There's a little box about 2 inches in the side that went into the basement that sweeps all of that up and presents it as a set of RESTful services. Whereas over in Cori, for example, we've now got hundreds of different legacy devices measuring this, that, and the other thing. There's a little box over there that sweeps it up and presents it. Whereas many of the system services, today they run across the street in a machine room over there. They could just as well, and often do, run up at Amazon in the cloud or something like that. Many of the applications will be sitting there on your phone or on things that are on the walls. Okay? Whereas recently, Therese and others deployed several hundred wireless sensor nodes throughout this building. In that case, there's a different little device that allows those to speak like they were a real network. And there's other drivers that integrate them in so that we can fold them in with some of these other things. So there's both a physical instantiation and a kind of lifting this up so it looks like all the rest of the stuff on the web. Okay so far? Okay. Just to ground that, for example, in this building, how much did we sweep up? There's about 6,000 sensing control points that were just built in as part of the building. We didn't have to deploy any new. We added a few hundred others. Is this a unique situation? Not particularly. Most large buildings, and there's about 10 million commercial buildings in this country, and the biggest of them almost all have digital controls. Even something as old as the Bancroft Library looks not particularly different. So there's lots of interesting sensors already throughout buildings. Wireless sensor networks and all the rest of the internet of all of that stuff is easy to deploy. There's all sorts of other sensors that you drop in throughout the space. There's far more, and of course we're all running around with a bunch of additional sensors and actuators in that space. And then there's the really important sensors, right? That what you hear, what you feel, what you see, what you smell are hugely important ones. Okay? So about 1,000 points times 10 million buildings, another billion or so points on the web. Residential, same story with more like tens of sensors, but 100 million, so another billion. Okay, so that's kind of the bottom piece of this thing that we worked on for quite some time, and I'll give you a little bit of stats on that. The question then is sort of what do you do with that? So what I'd like to do is spend a little time trying to flesh out what would be in this service tier. Okay? That there's very little question about how you elevate this up to where you could start to build services on top of it. What goes in there? Okay. So, I guess I illustrated a little more. So a piece of this, which is basically Stephen's PhD thesis, is recognizing that part of what's here is managing the flow of these streams, time series streams of information. So hundreds of thousands, perhaps millions of streams that are being published into some sort of store. Part of what's interesting is that almost all of these streams are time series, measurement of electricity usage or thermals or something else over time. And in order to understand what those signals mean, you have to capture information about them, which is the metadata, information about the data. This is the piece of this HVAC system measuring an air handling unit. Okay? Much of that is also rendered in various ways in applications. The most obvious is to graph it. Much more interesting is to manipulate it. As you look at embedded control and whatnot, then it's also about taking information and causing actions. I noticed I push a button, I want that light to go on. And that almost no physical information is useful in its raw form. So just like in many other empirical fields, you need to build in the ability to distill down from this raw stuff useful subpieces. Okay, so that's a piece we've been building for some time, just to give you a sense. Running on one little machine here, we have about 250,000 such streams. All of campus, thousands of points within certain buildings on campus, every ISO in North America, and we threw in Europe just for grins. We've had hundreds of points up at LBL as part of their miscellaneous and electronic loads. Meteorological data from every zip code that has a solar panel in California. You know, as you want to start writing applications that deal with this as a network. So this is doable, in some sense done. It's got interesting systems challenge of hundreds of thousands of things that are sort of trickling in, which you then go back and access as chunks of information over time, and you access a few of them. I'll touch on that just a little bit. Okay? But can we tackle this at scale? Absolutely. Okay? So that's kind of the next level. Questions so far? We good? So I was saying that some of what we were grappling with in here is how rich a structure do you need to describe that? The world, so there's all sorts of academic projects like this, and they produce stack feet of specifications that nobody implements. And we started with the NIST catalog, and that's grown to hundreds of elements where every company expands it to all sorts of features that are mostly there to keep others from implementing it. So initially, we were incredibly simple. Each point, 2-level structure. It had either it was sampling something over time, like a meter, like a gauge rather, or it was accumulating values like a meter, and essentially it said, here's a set of readings, very strict 2-level structure. As we did more of those deployments, we decided this was really inadequate. We needed a richer capability. So the basic notion down there at the bottom now is this is a resource-oriented architecture. It's a collection of series. So you can group them hierarchically. And if you think about something like the HVAC system for this building, we've got thermostats throughout. We have those glued together into some larger units. So the notion essentially is that each of these resources have both data and metadata, that the data is a collection of streams or other collections. And that gives you some of the hierarchical structure. Everything is uniquely identified, and all of the readings are time-stamped, and that's it. But now with that, you can build a very rich set of structure around it. So a lot of the question has been just how much do you carry in the metadata? How much of that gets inherited? So as an example, you might have a resource like something that is on the Berkeley campus on Soda Hall. It may be, in this case, a particular device, one that's manufactured by Dent Industries and is a Power Scout with a sample period that may be attached to a lighting circuit that serves certain floors. It may be looking at all three phases and delivering a true power measurement so that each of these streams are tagged with key value pairs so you can go back and understand some of it. Okay? And sometimes you get a new source that has, say, 5,000 points, like the BMS, and you want to preserve whatever structure went into that. Okay. And the other thing we discovered was all the interesting things for applications is not about walking down this hierarchy, but relating it to others. This, for example, captures how I did the measurement. I may also want to know where does that fall in space. It's within this campus, within this building, on this floor, within this room. How it relates to electrical uses. It's below this substation, inside this building, on the lighting circuit in this room. How do you bring those together? Okay. So the answer there was by just capturing the attributes, you could go back and build the hierarchies that gave you all of those other relationships. Okay. So that's, and Therese is a great example. She's gone around marking hundreds of these so that software could automatically build the larger relations out of them. Okay. And so down inside, if you were to look at any of these streams, what you see is all of this metadata that says this is what the time series means. Okay. So that's kind of the bottom tier. And I should be a little bit more careful because when I draw this box, what it really means is that there's a driver for some particular kind of device. There may be millions of instantiations of that, just like there's a driver for an HP printer, millions of printers. So what actually happens is there's a repository of a small number of device drivers. There's now an open source community writing more of those. So every time somebody shows up with a new device, hopefully only one person writes the driver once. When you plug in one of those devices, what you're actually getting is an instance of that running in your building somewhere. And there is the equivalent of your registry that captures how is that actually plugged into your... So any file, if you will, that describes the thing you're actually connected to, how does it fit in with the larger building? Okay. So there's a whole bunch of interesting problems from a computer science point of view about how do you build a high-performance time series data store that also supports rapid access to real-time information to control and utilizes that metadata, turning it around. There's a whole family of techniques in there about building that kind of store, and that's great. Interesting things that have come out of that. All of us take for granted now that there are databases under almost anything, and we have languages on top of them like SQL, so that we don't have to know much about them. There's some very interesting similar problems about query languages for time series store, where to make sense of what you're querying, you're walking down this metadata, and it's full of holes, and you have to resample it. And so there's this very nice piece of work to give you what you take for granted for all of that other information for physical information. Okay. In particular, what tends to happen is that to get anything useful, so what another piece of Stephen's work really is to build the kind of stuff you'd want to use out of the databases that exist in the world, where you compile this high-level query language down to this network of operators that integrates also some security checks before accessing it on Postgres. So I figured in this talk I wouldn't get into a lot of what's down inside there, other than to say almost all of what comes out ends up in this model that, in general, besides inserting a bunch of stuff, every time you try to make use of multiple things, you end up having to resample them in a common timescale, interpolate through holes. We do this millions of different times all over. That should be built into the platform so that, we all get benefit out of it, and now is. And then very often, those resampled and interpolated distillates we aggregate down. And so you want tools for doing that. Okay? So that's been done, and as a result, all sorts of applications got written on top, campus portals. This was, so the modern version of this one is now comfy, running in this building now that it went out to building robotics, that gives you personalized environmental control. We can't, I guess. That used to provide feedback back up to Domenico so he could see what was going on, which of the rooms were close, what people were saying. Lots of different applications at that top level. Okay. And so this world of building the underlying operator language is itself a neat piece. Okay. So what I want to do is move a little bit through to flesh out some of what's in these higher level parts besides that. Okay. So you're comfortable, for example, in this building, this little box essentially is pulling in the lighting system and the Siemens HVAC system. And I touched on occupant-driven control, wide guard bands to have greater agility, a variety of things. Here's an example. I want to deploy demand response on this building, which we did. Our goal was to flex 30% of peak in the middle. That's a nice example where there's a third party that's collecting information from the California ISO and delivering you notification of demand response event. There's a teeny little application at the top, a couple hundred lines of code that's taking the fact that we need to flex the building and causing changes of set points throughout in order to operate at a perhaps less comfortable, in this case, but doesn't have to be, and more efficient point. So, for example, here we are in the peak of summer. The blue shows what we would have expected to have spent on energy to maintain the environment. The red shows what we did. We did a little extra effort early in order to save a lot at the peak. A different example. It's the year of the wireless sensor networks. We deployed zillions of CO2 sensors. That's a don't care anymore. Wireless sensor networks are cheap by the dozen. You can bring in calendar. It's not hard to do that. What's hard is to actually integrate it into the building system and make any use of that information. So here's a little exercise. These days, Title 24 says buildings should operate on demand-controlled ventilation. So rather than blowing enough air to provide clean, fresh air regardless of the occupancy, you should have a CO2 sensor, and you should bring in more ventilation if you need it and less if you don't. So what's the aftermarket for buildings? Okay, easy to deploy the sensors. What do you do with it? In this particular one, which Jay Taneja presented, for starters, all decent resources like a room, of course, have an entry in the calendar, so you should sweep that up. Of course, we can measure the CO2, and we can blow air proportion to the amount of CO2. So, for example, before the meeting, freshen the room up. Bring nice, clean air, and during the meeting, modulate it so that you bring in more when you need it. And, of course, not everything's scheduled, so, react to that. All right, how does that perform? Here's a typical seminar room in this building, blowing 220 cubic feet per minute continuously, even when nobody's there. Here's the CO2. Notice still taking excursions outside of the 800 parts per million. In fact, if you're wondering, I think most rooms, especially classrooms on campus, especially in the afternoon, way exceed this if you're wondering why you fall asleep in lecture. Sometimes exceeded by a lot, okay? As opposed to, same hardware, just a little more intelligence. Now you're typically blowing 30 cubic feet a minute. You blow a lot more when you need it. You blow it in advance and you almost never go out, okay? Result here, saving 85% of fan power for a considerably better environment. Okay, so you don't actually have to make this false trade between energy efficiency and performance. Okay, so let's flesh out a little bit more of what's above there. One of the notions, then, as you start to get into this, all of a sudden the idea that applications for the building is a reasonable thing. In fact, many completing applications is a reasonable thing. Those applications are using common resources and needs to take action across multiple resources. So in the computer systems world, databases, for example, have a notion of a transaction, which is something I want to make multiple changes to the state of things, and I want the behavior to be all or nothing. So a piece of work is to try to understand what would be a transaction manager for buildings. And I won't go into this in a lot of detail other than to suggest that there is one, and that in buildings it's rather different than in a computer system. For example, a database transaction, you go to your ATM machine, you start to withdraw something, something crashes, you don't get your money. You want to make sure that either you get your money, the debit to your account. You get both of those or neither of those, not one of them, right? The bank has a preference on which one. You have a different preference. They're both bad, okay? So the notion here is you'd like some of that. I'm going to touch many points, but failure might happen, and then how do I roll back, okay? So the two key concepts in here. One is every time I'm operating the building in some optimized form, I'm doing it under a lease, some kind of a keep alive, we call it, that the communication that's required in order to operate in that mode is still there. And should it fail, so you notice a lifetime, very much like your DHCP, how long you have an IP address. If that fails, I've also articulated how I fall back. Okay? So that as part of moving the building forward, you have to constantly building in resilience. There's a little bit of machinery to do that. Okay? And should either you stop paying attention, I walk out of the building, if I'm not, it should move back to a safe state, or something bad happens. The other, of course, is there's a physical system under there. And so I've taken your simple PID controller, for example, and pushed the state way outside of its normal operating range in order to be more agile and more efficient. And some failure happens, and I say, here, you got control back. And this is an example of a PID loop saying, oh, my God, I never expected to be here. And so it starts, whereas you may have to gracefully phase in one control regime to another. This is Claire and friends will help us sort out how we should really do this. One of the things you want to develop model predictive control, the first thing you have to do is build a model. In order to build a model, you have to perturb the system, the building. So in particular, Francesco Borelli's team wanted to do step tests throughout this building. Here, go move the temperature like this. So we built a tool where they could script the building. And then we set rules for when they got to script the building, which was a nice example to develop, under what conditions can you do what? So this is part of the things you do as an application are within an envelope that controls it. If we could do that, we could do almost anything else. So that was essentially the underpinning for doing things like these personalized control that allow individuals to say, I'm in this room and I want a puff of cold air right now. Why? because I want a puff of cold air right now, right? This isn't, I want to send email to the building manager, as good as Domenico is, that say, please, would you change the set point? I'm not trying to change. I want the building to respond to me, just like any other kind of a human interface. Okay, so those kind of things caused us also then to begin to understand how to develop an authorization service. And this is an interesting design trade-off of, can I get pre-authorization? Do I have to check everything? Where we evolved to here was a kind of structure where the application would go and request authorization for a certain set of resources under a certain bound. And the system would make sure they stayed within that. And if they tried to go beyond, Francesco's team, tried to heat the auditorium up to 90 degrees, we would abort, fall back. Okay? And actually, any guesses on what the approval mechanism was for that authorization? Well, we did the simple thing. It showed up on Domenico's screen, and he could push the button that says, that's okay. Okay. We could automate Domenico a little further. But that was another piece to sort of build into here. So this is showing that BLAST app that I sort of talked to you about. It would identify certain resources and a temperature range that it was going to flex the building between 65 and 75. It gets back an authorization token, something encrypted. It can then use that now, and as long as it stays within it, it has authorization. What I've thrown in here is an example where, in fact, I've aborted it, and you can see the system automatically reverting back into the non-blast mode. Yes, early versions of this, you get halfway through, you open everything up, you blow cold air, and then you walk away, and you're blowing cold air for the next, all night long, right? Okay. We got to the point where we could do anything we wanted for a building. The question is, could you write an application that you could run on lots of buildings, right? 5 million of them in this country if it was commercial. The challenge in there is all about portability. Different protocols, different devices, different control schemes, and of course every building cited different, designed different. So, you take a problem. Here's another one we did. You're supposed to have a certain amount of fresh air as a function of occupancy. If you're operating a building efficiently, there's a flap that determines how much fresh air is in the mix versus recycled air. How can you possibly be actuating what's coming into the room to give a certain amount of fresh air with not understanding how much fresh air is in the mix? So this is 2 different controllers out of the hundreds that don't know about each other. We could integrate them together, and we did. How do you do that optimization on any building? As an example. Okay. So different kind of buildings, different underlying ductwork and systems, different control loops. This is the code for buildings. It's worse than assembly language, at this very low level. So, the 2 key ideas there was raise the level of abstraction so that applications are working at this semantic level. I want to talk about rooms on the top floor, not this particular lighting relay. And the second was build up this hierarchy of drivers so that the operations you're doing are at a high level. I want to turn the lights on 100%, not manipulate a bunch of points I don't know about in order to accomplish that. Okay. So those ideas were fleshing out a hierarchy of driver and this kind of entity relationship graph that moved us up. Okay. So I touched on this earlier. Actually doing something in cyber-physical systems is often about relating these different concepts. So here I've tried to illustrate the spatial domain from the lighting domain, from the electrical domain, from the HVAC domain, and a kind of structure that would tie them together. Okay? So these different domains, you want to be able to say, give me all of the lights that light room 123. or give me all of the rooms that are served by the same air handler as what serves this particular area. Okay? Position-independent code. The result of that is instead of this kind of stuff, something like that whole building optimization ends up being a trivial piece of code. Give me all of the dampers in this area that are served by that economizer, have their behavior connect. Okay? And this is an example showing a couple of things. One is you'll never move things forward if it takes you a year to get enough statistics to see if the change you made was helpful. So grad student gets to do an experiment on the weekend. It's a weekend that's never been seen before. You've got to learn from the past so that you get a good estimate, and then you can have some confidence that the gain you made was actually positive. Okay? I did buildings. This same technology we've been using for synchrophasers, which is getting wide area phase angle measurement and looking at the difference, partly because phase angles tend to diverge just before very bad things happen. This was a different example of sort of pushing some of the underlying infrastructure to get very tight time synchronization. Okay, so we're at this really interesting time. And I realize that this is not exactly a very precise graph, but, it used to be that it costs us hundreds of dollars to connect things, and we understood that there's a point where when it's kind of $1, you connect all the people, and, this is, so even though this is an old one, we're kind of at that point, okay? For example, in October 2012, the internet light bulb came out. Okay? Today, LEDs are everywhere, and all of them have a network backend. 2013, the big rage was Nest, which had a big 2014 exit, but the bottom's already fallen out of the network thermostat market. Everybody has network thermostats everywhere, and of course, it's all about the wearables and the ambient displays and all the rest of it. There's no question. So a different connection here. You're all used to a thermostat, right? Imagine if what you're really trying to do is control the comfort in a building. Imagine if you had a comfort dial. What would you set it to? I mean, obviously, you'd set it to 11, right? Or something. But what would that even mean? So, today, you have a space like this, and you have a few of these, right? And you're trying to derive comfort from... So this was a nice connection back into our friends in the Center for Built Environment, Ed Ahrens and team. And another one, actually, so they've been busy doing these human comfort models. And what happens when the furniture starts to give you a personalized environmental comfort? And so he puts this warm thing in a very important part of the seat and some fans. It's amazing. And he understands that changing perception is very different. So we've been playing with this and with all of those other things to begin now moving beyond the building to make sense of the Internet of Stuff. Everything is networked, even the furniture. And in fact, if you think about that, now you have a gauge on comfort. If nobody is overriding their environment with their chair, the environment's comfortable. If you're overriding it because of different, or because you have a diversity of where that wants to meet, or because the building is trying to flex and you're trying to... So this is an interesting world. Okay, so this has caused us to dig in and think harder about some of these pieces, okay? So a sort of obvious part is you need the equivalent of plug and play for this kind of device. So in fact, now we bring all these god-awful new devices into the lab. They attach to a network like most things do. The first thing is to figure out what the heck is that. So out there, I've tried to indicate there's some repositories. One is a detector repository. So you've got some detectors. You say, oh my gosh, that's a Honeywell thermostat. That's what it is. Great. I'll go out there and grab a driver for that and build in an instant. So now you can plug things in. You can discover them. You could start to make sense of them. So I can build my registry and start doing all the things we talked about, publishing all that data and so forth. What this caused us to do is to go back and rethink some of those assumptions we made at the beginning of whether we really could get by on a much more limited pub-sub. And how about that? In the 20 years, that big hunkin' MQTT that used to be on the mainframes inside of IBM, now there's an open source lightweight version because, of course, these little embedded devices have more oomph than those mainframes used to. So this is a very rich open source environment. Okay, so we started taking that and moving it forward. Here's just a little example. I got a bunch of things that are like switches, and I have a bunch of things that are light. Here's a little piece of code. You can imagine there's some GUI that connects now which light is connected to which switch. And here's a trivial little piece of code that says if this switch goes on, well, then turn whatever lights were mapped to it on. So now, very elaborate control ends up being very simple. Here's a different one that says, oh, it's a dimmer. You push the dimmer, and now I start fading it off like those fancy things you get from. Okay. But it's been an interesting week. Yesterday we learned that the hackers are coming in through the vent machines and whatnot. So part of, a little earlier, small little event for Target. Of course, this world, it's not like the control that we can within a building. So we've utilized the structure of a building to guide a lot of the authorization. So I guess I don't have time. This actually is the phase difference between the substation up at Grizzly Peak and two things down inside of Soda. That's true. That was all to say we've been thinking much harder about these distributed trust and authorization. So let me give you a little example, and this will be my last one, and I'll close. I got a bunch of this stuff. I have a lighting application that is trying to glue this switch to that light. And what this says is the lighting application trusts the switch and it trusts the light. Okay? So all that application is doing is the switch is publishing to the light through a broker. And the basic thing is the application has to prove to the broker that it has authorization to publish the switch events to that light. And of course, this is inside a world of resources. There's somebody that owns those in Berkeley, so the broker has to resolve a trust relationship to prove that it has that. But of course, campus has delegated trust to a campus manager who's delegated it to facility managers, and the facility manager, of course, trusts the devices it put in and the application that he installed. So the key is that you can walk through this trust chain and prove by providing a little signature that this application has rights to do that. So can we build up a more robust trust model? Okay. So that's the overall picture of where we got to for BOSS. Obviously, it's all about scale, heterogeneity, dealing with uncertainty, and maintaining that sense of empowerment. And I'd like to stop and take a few minutes for your thoughts. And yes, I was a bad boy and I ran over. Sorry. Carlo.
Sensors we now have in our engineering buildings, can we actually tell how many people are in those buildings, where they are? Or is that still kind of a dream at this point?
Yes and no. So the question is, how much do we really want to know? So you can tell a lot about occupancy. Technically, you have the ability to tell a lot more, but it's not clear that you want to actually get to the point where you know. You could imagine, much as you have a relationship with your grocery store, where you give up some of your privacy in return for a discount on your food, you could imagine you should be able to give a little bit of your privacy up to the building in order for it to provide better services. But that's a little different from all of the buildings tracking everybody down inside. So that's a very delicate one. For example, some of those techniques Based on CO2, can you estimate occupancy? Yes. Based on cell phone activity? Yes. Based on network activity? Yes. There's all sorts of ways where you can start to build population maps.
Could you use that to actually turn off the lights?
We could. Yeah, and obviously motion sensors and a lot. So, yeah.
So in a resource constrained world,
yeah,
where you want to do this, and okay, fine, I have these controls, I set my lighting, or
yep.
But it's resource constrained, so not everybody can do what they want to.
So
how are you going to? Must that problem be sort of centralized? Is there a decentralized architecture to manage resource-constrained work?
Yeah, so two pieces of that. Don't confuse conflicting demands and conflict resolution from resource constraint. Right? The fact that we have different applications, maybe even different goals, we have to resolve that. That has nothing to do with little device and whatnot. Everything I presented here, of course, architecturally it says, I don't have a strong position whether I distribute things or I centralize them. And that's the right thing to do because there's different trade-offs. So that's architecture versus organization. In the vast majority of cases, you can push out responses to events and whatnot and decentralize those. So a vast amount of this, and even if you take something that's centralized like that time series, of course you end up distributing it over a bunch of things in the cloud. So there's all sorts of places where you can employ replication and distribution for improving latency or improving bandwidth. But the question of conflict resolution is in some sense a much more fundamental one. Right? So I'm not terribly worked up about the particular one of what if I don't have enough computing power in the sheet metal because I have a lot of computing power in the sheet metal. The place where I've found that we move things up and centralize it is because you actually want history to guide you. Right? It has much more to do with the information than
There's not enough power in the grid.
Yeah.
And everybody wants comfort, and not all the you aggregate everybody's comfort.
Right.
And somebody's got to give.
Sure.
So is that necessarily a centralized issue?
I don't believe it's necessarily a centralized one, or that this suggests that it forces you into that. I mean, the hard part there is I have to bring that up. I mean, the internet is not centralized either, and it's a lot bigger than the grid, right? Now, actually resolving who gets what, the more important part of that is once you say, Kameshwar, you've decided to step back, how do you actually respond to that? That's really what this is getting at.
Last question.
Yeah.
Supposing you had no limitations on the kind of data you can gather at the bottom level, it would seem that rich or high-density signals like audio-visual, cameras, surveillance cameras, and so forth could be helpful in occupancy data. Does the SMAP driver have to do a lot of abstraction from those signals in order for the system to use it?
Yeah, great question, thanks. Because in some sense, that is what we decided explicitly not to try to go after was audio and visual because it looks like Netflix. And that's where all of a sudden everything changes because your streams are each and every one of them many megabits per second. So then the question is, do you do that locally and you deliver events? The other is, oh my God, in terms of privacy, security, and so much else, it completely changes. So it's true, some of the grad students have done experiments like, let me turn my phone on so that it's recording of audio all the time as I walk around. And can I use that for localization? And how do I feel about that? So it's slightly convenient, but I think it's a much deeper one. So no, this is really looking at things that are on the order of hertz, maybe tens of hertz. And then you flip over into this other world. And those are, 3 or 4 orders of magnitude really do make a difference.
Thank you, Dave.
Certainly.